Howdy, howdy. This is Mr. Potter. In Chapter 6, we take a different viewpoint of the derivatives that we've been talking about since Chapter 3. And two of the tools that we'll be using at the beginning here is the concept of a differential equation and also the idea of a slope field. A slope field is a way to visualize the derivative in a way that we haven't really talked about before. A differential equation, on the other hand, is something a little bit more specific. So a differential equation is a relation between an independent variable a dependent variable and its derivative. So what we're going to be dealing with is we're going to be dealing with x, y, and dy dx, or we'll be dealing with t, velocity, and dv dt. So we'll be dealing with some function and its derivative in a relation. So I might have something as simple as this: dy dx equals 3x squared, which we'll be talking about in just a moment. Or I could say something like dy dx equals e to the x. And both of these are fairly simple and straightforward differential equations. But it can be a relation. And so when I talk about a relation, I could have something like xy prime plus y equals 2, or y equals x y prime. These more involved, these more complicated parts. And in reality, differential equations is an entire branch of mathematics, which we will barely touch upon in this class. We'll only be dealing with a certain category of differential equations called separable differential equations. And we'll explain what we mean by that later on in this chapter. For now, what you need to understand is that a differential equation is a relation. And we're going to be dealing with an independent variable, a dependent variable, and its derivative. And so we're going to be dealing mostly with differential equations like these top two examples. So that's the first thing that I want to talk about. The second thing that I want to talk about is a slope field. And the whole idea behind a slope field is a slope field demonstrates the slope at a lattice point on an xy coordinate system. So what's going to happen in these situations is given some differential equation, like the one that we talked about just a few minutes ago, dy dx equals 3x squared. I can draw a coordinate axis, and I can talk about demonstrating the slope at each of these lattice points by drawing a line segment that has that slope. And so, for example, at x equals 0, my slope is going to be 0, because 3 times 0 squared is 0. And so that means whenever x is 0, my slope of each of these demonstrative segments is going to have a 0 slope. In a situation where x equals 1, my slope would be somewhere in the neighborhood of 3. So it's going to be a fairly steep line at x equals 1. And I can demonstrate this for all values of x equals 1. And of course, that also holds true for x equals negative 1. I'm still going to have that same slope of 3. And I can talk about what happens at x equals 2. My slope is going to be 12. So it's almost going to be vertical. It's going to be a very, very steep line, almost a vertical line. And of course, the same thing is going to happen at x equals negative 2. So what happens is my slope field demonstrates what the slope is for general points in my xy plane. Now, one of the nice things that we can do with slope fields is, starting at some particular point, say this point here, I can follow the contours of my graph. I notice that I'm increasing rather steeply. I'm coming to a horizontal tangent, then I'm decreasing rather steeply. can actually draw a solution to the differential equation. I can solve a differential equation graphically using a slope field. Now keep in mind, the whole idea by a slope field is that this is going to demonstrate all of the possible slopes. So I've got a curve that passes through a given point, but if I was given a different point, say a point over here, what I would find is that I'm going to end up with a different curve. And so what also is nice about a slope field is it doesn't just demonstrate one solution, but a slope field demonstrates a family of solutions. So in other words, there's not just one function whose derivative is 3x squared. There's a whole bunch of functions whose derivative is 3x squared. I kind of have one function here, the one in purple, that looks an awful lot like x cubed plus maybe 0.5. Because I know that the derivative of x cubed is 3x squared, so I know it matches this. And the derivative of a constant is 0. A constant isn't going to contribute anything to the derivative. And so that means that if I was to have a vertical translation, something like this, x cubed plus 2, which appears in this light blue, this is the exact same derivative. Both of these functions that I've drawn have the same derivative, have a derivative of 3x squared. So both of these curves that I've drawn are solutions to this differential equations where y prime equals 3x squared. So a slope field really helps us in two ways. One, it helps us to demonstrate the slope at any particular x and y coordinate. But more important than that, it helps us to find a graphical solution to a differential equation. In this case, it's rather easy to think of functions whose derivative would be 3x squared because we've seen the power rule so much. It may not be as easy to think of a situation where if I'm looking at a function like dy dx equals x times y, when I actually see it as a relation rather than seeing it as a function, it may not be as easy to find a function whose derivative would satisfy satisfy this differential equation. But it's relatively easy for me to draw line segments whose slope are the product of the x and y coordinates at a particular point. If I wanted to take a look at the origin, I know 0 times 0 is 0. As a matter of fact, for any y equals 0, 0 times anything is going to give me 0. So that means for any point on the y-axis, my slope would be 0. For any point on the x-axis, my slope would have to be 0 as well. So a 0 slope line segment would demonstrate any point where it's intersecting the x or y axis. And that means wherever my graph hits the x or y axis, I'm going to have a horizontal tangent line. If I take a look at the point 1, 1, I know that 1 times 1 is 1. And so I'm going to end up with a fairly straightforward line segment whose slope is 1. But if x is 2 and y is 1, I'm going to have a line whose slope is 2, a little bit more steep. And over here, where x is 1 and y is 2, I'm going to have that same line. These two line segments should be parallel. And if I go over to 2, 2, I'm going to have something that's quite a bit more steep. And the same thing's going to happen in this third quadrant, because negative times negative would give me positive. So I'm going to have these same four slopes in this fourth quadrant that kind of meet this curve. In the second quadrant over here, something interesting happens. I've got negative 1 times positive 1. And so I end up actually with a reflection. So just looking at this and knowing the nature of negative numbers, I can see that a solution to this graph is probably going to be even, because I see that reflection across the y-axis. And of course, the fourth quadrant slopes are going to be almost the same as my second quadrant slopes. And so, given this slope field, given this demonstration of what the slope looks like at any particular x and y, I can start at some point on my curve and actually come up with a fairly good visual solution, as long as I follow the contours of my graph. I should come up with a fairly good solution. And of course, notice that the only difference between the solutions that I'm dealing with are where my graph crosses the y-axis. In other words, the only thing that really determines a solution, almost determines a solution uniquely, is where it hits the y-axis. If I'm given a point, some point, as long as I'm given a point, I can find a graphical solution that fits the contours of my slope field. If as long as I'm given some initial value, as a matter of fact, there's a whole segment of differential equations called initial value problems, and we'll touch a little bit more on this in tomorrow's lesson. The key thing here is that I can do slope fields for relations. So let's go ahead and take a look at this, where I've got dy dx equals x plus y minus 1. So it's not really a multiplication situation here. It's a pretty straightforward summation. So if I take a look at this coordinate axis, I need to look at values like the origin. If I substitute 0, 0 in here, I end up with the slope of negative 1. And what that means is that at the origin, I'm going to have a line segment whose slope is negative 1. But in reality, if I was dealing with negative 1 and positive 1, that would also have that same slope. Or negative 2 and positive 2, which means along this minor diagonal, my slopes would all be negative 1. And if y was 0 and x was 1, I'd have 1 plus 0 minus 1, so I'd have 0. And I find parallel to this line of negative 1 slopes, I'm going to have a situation where I've got a line of 0 slopes. And if my slopes were negative 1 here and 0 here, then I think if I'm dealing at the point 2, 0, my slope is going to be positive 1. And I'm going to have another set of parallel lines where I've got a positive 1 slope. And by substituting points, I can actually get a fairly good contour of my graph. Here my slope was 0, here my slope was negative 1, so now I'm probably dealing with a negative 2 slope parallel to these, and a negative 3 slope. And the idea here is not that I want to actually slope the actual, I'm not that I actually want to graph the actual slope values, but what I want to look at are the relational slopes. In other words, I should see the slopes steadily getting larger as x increases. I should see the slopes getting larger as y increases for a constant x. And as I look towards the third quadrant, as I come down here, I should see the slopes getting more and more negative. And I notice that I have several different solutions. It looks like I'm going to have a horizontal tangent and then stuff shooting up, or I can come down a little bit more to a horizontal tangent and shooting up, or I could have on this side of the line, I notice that they tend to go towards negative infinity. So these are what my family of solutions for this differential equation would look like. A differential equation that we, in the scope of what we've learned so far, we have no way of actually solving this, but this does give us a very good idea of what solutions would look like very esoteric functions here that we're dealing with. So I want to do one more slope field here. I want to do a very, very simple slope field. dy dx equals x. So in other words, my slope at a particular point is only determined by my x coordinate, and it's equal to my x coordinate. So if I'm dealing with points on the y-axis where x equals 0, I've got slopes of 0. If I'm dealing with x equals 1, I've got a slope of 1. No matter what my y-coordinate is, my x is solely determined my slope. If x is negative 1, then my slope is negative 1. If x is 2, then I'm going to have quite a bit of steeper here, steeper than the lines that I've already drawn. And if x is negative 2, then my lines are going to have a negative steep slope. And on the AP exam, you're going to be drawing lines, and they're going to be looking at the degree of steepness in comparison to other points on our slope field. Now, if I start looking at solutions, what's happening is my solutions are decreasing, and then tangent, horizontal tangent at x equals 0, and then increasing, decreasing, horizontal tangent, and then increasing. And one of the things that I'm looking at here as I graph these lines are these solutions, this family of solutions certainly look a lot like parabolas. And if I had to come up with some function whose derivative was x, I'd be thinking of it in terms of the power rule. So I know that the derivative is x to the first power. And I know that if I wanted to work backwards, I know that to take the derivative of something, I bring the exponent down. So I multiply the coefficient by my current exponent, and then I decrease the exponent by 1. So if I wanted to find a way to work backwards, what I would do is I would find a way to increase my exponent by 1. Take that second step of the power rule and work backwards, and then divide by my new exponent. So in other words, now I'm looking at solutions where my solutions would be x squared over 2, or 1/2 x squared. And my family of solutions are going to fit this build. 1/2 x squared, but notice that the difference between each of these solutions is the constant where I cross the y-axis. The difference in these solutions are my y-intercept. And I know that if I was to go back and take the derivative of a constant is 0. So I know that a constant is not going to contribute to the solution. So when I talk about a family of solutions, I'm talking about all of the different constant values that could go in to make sure that I can hit every single possible point that a solution could hit. And this function that we've come up with here, since I've taken the rules for finding a derivative and worked backwards, we're going to call these antiderivatives. And so this really is going to be the focus of chapter 6, finding solutions to these differential equations and finding these functions that are antiderivatives of given functions. Because these antiderivatives are our solutions to differential equations. And the slope field is the major tool for finding a graphical solution to a differential equation, as opposed to an analytic solution. But we should find some agreement between them. So that's our introduction to chapter 6. This is Mr. Potter. Thank you for watching. Have a great day.